All right, ladies and gentlemen, class recording for today has started. So yesterday, we introduced the concept of a conversion factor. We said that conversion factors allow us to change the units of a measurement without actually changing what that measurement is. Right? We're just representing the same thing, but in a different way. It gets rid of bad units and leaves us with good units. And so, why don't we just go through an example, because that'll be a good way for reminding us what we did before. So let's take a look here at question number 3 down at the bottom. Excuse me. All right, so it says, if a football player is tackled 1.7 feet short of the end zone, how many more yards does the team need to get a touchdown? All right, so first, we said that when we're solving this problem or any type of problem, what's the first thing that we should identify? What are we trying to answer? What are we trying to find? So, Will, what are we trying to find in this problem? How many more yards, right? How many more yards? So, in this case, if we're talking about equating this to like the scientific method, right? The question that we're asking is how many yards do we have to go? Okay? We've identified what we're looking for. What's next? Well, what's the next step in the scientific method? Hypothesis, right? What is our hypothesis based on? Facts, laws, and theories, right? Things we know. So what's the one thing that we know about this distance here, Kareem? Okay, we are 1.7 feet short of the end zone. So that's the thing that we know. Okay? Now, at the end of this problem, that distance isn't going to be any different. That team will still be that distance short of the end zone. We're just representing it with a different unit. Right? Conversion factors don't change the value, they just change how we're representing the value. Okay? So we're going to need a conversion factor here. Said, if you want, you can put that original number over 1 just to turn it into a fraction, if that makes a little more sense mathematically in terms of multiplying the fractions. And then a conversion factor itself is a fraction. So, times sign fraction bar. Okay? Yesterday, when we were setting up conversion factors, I said let's start with units, right? What unit needs to go on the bottom of this conversion factor? Feet. Feet should go on the bottom of this conversion factor because conversion factors get rid of the unit that we don't want. So in order for those to cancel, we're going to put feet on the bottom, right? Then, if conversion factors get rid of units that we don't want and leave us with units that we do want, what unit should go on the top? Yards. Okay? Yard is going to go here. What did we say has to be true about the top and the bottom of a conversion factor? They should be equal. In essence, by making the top and the bottom of the conversion factor equal, we said that we're multiplying our original number by 1. Which doesn't change the value of the original measurement, it just changes how we're representing it. So, what numbers do we have to put in here to make the top and the bottom equal to one another? Okay. 1 yard, 3 feet. Okay? 1 yard, 3 feet. As far as the quiz goes, I just wrote the quiz this afternoon, so, no. Oh, the conversion that we have to do is a conversion that do we know how many seconds are in a minute?
70.
Good. Yes. Yes, 70 seconds in a minute. So you do that on the quiz, okay? So, long story short, if there is a conversion factor that I don't think that you might know automatically, like this one, I don't know if everybody knew that there were 3 feet in a yard. I would include that information in the problem for you to set up the conversion factor. So even if you didn't know that, you could still set up the conversion factor. But these two things need to be equal. All right, now it's time for some math, right? All right, we have feet as a unit in the top of this fraction here. We have feet as a unit in the bottom of this fraction here. What's going to happen to the feet, top and bottom? They're going to cancel each other out, right? So feet and feet go away, right? Not the number, just the unit. Okay? Now, what's the only unit left in our problem? Yards. Yards, and that's good because that's what we want. Okay, now it's time to do some more math. Okay? Here, we are multiplying fractions together. In order to multiply fractions together, what do? Multiply the tops, multiply the bottoms. One thing you shouldn't do here is cross-multiply. Okay? We cross-multiply when two fractions are equal to each other, right? Then we can cross-multiply. Here, these two fractions are not equal to each other. Don't cross-multiply. I see students do that sometimes, so I'm just warning you, okay? All right, so let's go across, right? So we got 1.7, no unit because we canceled feet, times 1 yard. So that means that we end up with 1.7 yards on the top, right? And then on the bottom, we have number 1, no unit. Number 3, no unit. So that's 3 on the bottom. Okay? So here, if I remember correctly from this morning, is that what we get when you plug that in your calculator? 0.5666666, right? Yep. All right, now, last thing, right? Let's round our answer to the correct number of significant digits. We said, I mentioned yesterday, that when we are doing conversion factors, we don't worry about the numbers in the conversion factor. These aren't measurements, these are ratios. These are exact numbers, they're equal to each other. So we round our answer to match the number of significant digits that our original measurement has. Our original measurement was 1.7 feet. How many significant digits in that number? 2. 2. So we need to round our answer to 2 significant digits. Okay? Is that 0 significant?
Yes. No.
Yes. It's a no.
There is a decimal point, but it's before the decimal point. That means that 0 is a placeholder. It is not part of the measurement. That 0 is not significant. Beginning zeros are not significant. All right? So the 5 is going to be significant. Then the next 6 is, but what comes right after that 6?
6.
Another 6, so what should we do?
7.
All right. 0.57 yards. 0.57 yards is the same distance as 1.7 feet. We're just representing it differently. All right, good there? Okay. Like I said yesterday, the intention of doing these problems is not so that you learn how to convert feet into yards. The intention of doing this problem is to set up this conversion factor, practice setting up where the units go and how the top has to match the bottom, so that when we encounter situations where we're not as familiar with the relationship between the numbers, we can still solve the problem. We can still figure out what we're trying to look for. And that leads us into today's discussion, and that leads us to start talking about counting atoms. How do we know how many atoms there are if they are so small? And it starts with a relative mass scale. First, what do relative scales tell us? They compare things, right? If we know the comparison between two values or between two measurements, we can use that to count. For example, in the bean lab you guys are working on or just finished up, we set up a relative scale. And it was all based on, for most of you, the white bean, right? The white bean was in the middle. All the other values were compared to the white bean. If we know how much a certain number of white beans weighs, we can figure out how much the same number of a different bean weighs because we know how the individual beans compare to each other, right? Does that make sense? If we know that 300 white beans weighs a certain amount, and kidney beans are 2.5 times white beans, if we have 300 kidney beans, they should weigh 2.5 times 300 white beans. That only holds true, though, if what has to be the case? Not sort of the same size. What do we have to have? The same
Mass.
Wait.
the same number, right? We got to compare 300 white beans to 300 kidney beans. We got to compare 500 white beans to 500 kidney beans if that relationship is going to be true. Okay? Does that make sense? Okay? All right. We've discussed relative mass scale before. It's atomic mass. What is atomic mass a relative scale compared to? Or what does atomic mass compare things to? Carbon-12. It compares the size of atom to the carbon-12 atom. All right? So, that being said, right, let's say we have element Z, okay? There is no element Z on the periodic table. I'm just using that as like a generic element, okay? Element Z has an atomic mass of 60 AMUs. What is that telling you about element Z? It's 5 times bigger than carbon-12, okay? Good? All right. That being said, if we put, let's say, 1,000,000 carbon-12 atoms on the balance and got a mass measurement, if we put 1,000,000 atoms of element Z on the balance, how much should it weigh? 5 times whatever the carbon-12 weighs, right? As long as we had the same number, that relationship still holds true. Good? Okay. So, with that being said, atoms themselves are really small. Duh. Right? Those numbers are the actual measurements of the mass of a proton, of a neutron, and of an electron. It's scientific notation, right? 10 to the minus 24th power, meaning which way would we move the decimal if we wanted to move it back into decimal notation? We move it to the left. A proton has a mass that has this number attached to it, but there are 23 zeros in front of it, right? Even a big atom like uranium that has 92 protons still has a super small mass. So using these values to actually count or measure atoms isn't really practical, right? That's where atomic mass comes into play. If we can only weigh one atom, like carbon-12, and we know how the other atoms are all related to it, we don't have to measure every single time. We can just use that relationship. Because as long as we have the same number, the relationship holds true. Okay? All right. So, atomic mass is relative scale for atoms, comparing all atoms to carbon-12. And we set a value equal to 12 for carbon-12, right? Good? Yes? I don't think you had to fill anything in yet on your outline yet. Okay. All right, so here's what happens. Average atomic mass. Average atomic mass is similar to atomic mass, but it takes into account the fact that we have more than one isotope of the same atom, right? Carbon-12 is one kind of carbon atom, but there are other types of carbon atoms, like carbon-13 and carbon-14. And so, we take into account all of that information, the individual mass of each atom, and then how much of each of those atoms there are. Or I guess I should say the individual mass of each isotope and how much of each isotope there is. And this is just stuff that we did earlier in the week, right? Hopefully, this, as you're writing this down, right, this looks familiar. And so, on your outline, the next line letter C, right? Roman numeral number 3, letter C, right? The relative scale for counting atoms has been used based off of the standard blank isotope. Which isotope do we base everything off of? Carbon 12. Okay. So yes, it compares atoms to atoms, but we can also use it in terms of counting, right? All right. So here's what, in essence, we have done. Okay. Like we said, if we put a certain number of atoms on the balance, the relationships of atomic mass, how big those atoms are relative to carbon 12, will still hold true as long as we're talking about the same number of atoms. Okay? So, here's what we do in order to count our atoms. Okay? Now, I'm saying count in the quotation marks around counting. We're not actually counting. Okay? But if we put enough carbon 12 atoms on the balance so that it weighs exactly 12 grams, okay? Hopefully that number looks familiar, right? That's what we do as far as counting is concerned. Oh, sorry. Ah. The number of atoms, I think that's the next thing on your top, right? The number of atoms. Okay. Did we skip one? Oh. Yeah, I don't, that was the one. Okay, sorry. I don't know why there's an extra line at the end of letter D. I don't think that should be there. Okay. The 12.00 grams that you fill in the next part is the end of that line. So, exactly, like 0.00 grams. Oh, sorry. God. There it is. So, yeah, at the end of letter D, I don't know why there's that extra line there. You can just like nothing fills into that spot. So you can put a period if you would like. Yes. All right. Everybody got D. Everybody got D written down. Okay. You don't have to worry about it. We did something similar to this in your bean counting lab. We figured out the mass of 300 white beans. And then to count 300 kidney beans, we didn't individually weigh the kidney beans. We just multiplied the mass of 300 white beans by whatever the factor was for kidney beans. All right? And then when you actually counted them, did we get 300? In a lot of cases, no, because what was the problem there? Why didn't we get exactly 300? All those beans are a little bit different size, right? And then not all of them are exactly the same, okay? All right. When we count out a specific number of carbon 12 atoms, enough carbon 12 atoms that it would give us a mass exactly equal to 12, the number of atoms that we count out is that number up on the board. 6.022 times 10 to the 23rd power. That's the number of atoms that we will use to compare all the other atoms to carbon 12. That number, 6.022 times 10 to the 23rd power, is called Avogadro's number or Avogadro's constant. Not avocado. Avogadro. Avogadro's great-great-great-great-great-grandchildren wouldn't appreciate calling him avocado.
I mean, he was my great-great-great-great-grandpa. I love him all the time.
Just think though, if you were his great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-great like a name like Avogadro, you would literally be called avocado for the rest of your life.
It's fun. It's much more fun to say than avocado.
Yeah, for everybody who's not named Avogadro.
That would definitely be the
So that you would like, you'd go to the bank and they'd be like, hey, what's your name? Avocado. Avocado? Like, no, Avogadro. Like, so can you spell that, please? It's like avocado but with a G. Yeah, there's an R in there too. But Anyway, all right, so this number is important. As long as we have this number of atoms, all those relationships for atomic mass on the periodic table would still be true, right? If we had 6.022 times 10 to the 23rd atoms of element Z, right, we talked about element Z before, yes, right? It would weigh exactly 5 times this, because we're talking about the same number of atoms. That number of atoms, the same number of atoms contained in a mass equal to the average atomic mass we call the molar mass. Show you in just a second why it's molar. It's the same number of atoms the same number of atoms contained in a mass equal to the average atomic mass for each element is called the molar mass. All right, good? So, Hannah, why is it called the molar mass? Because that number of items we refer to as a mole. I don't know why it's actually called that. All right, so the mole is our standard SI base unit for counting. First, if we set up a base unit for measuring or counting things, what does that mean? Or what should be true about the base unit of something? Not necessarily. If this is a meter stick that we use for measuring things in meters, what should be true about all the meter sticks out there in the world? They should be the same, right? A standard base unit should never change. Meaning, if we're going to count something, we should always count the same number of items. That same number of items is called a mole. The mole always has the same number of things. That number is a really large number, 6.022 times 10 to the 23rd. Anytime we describe something as being a mole, we are always referring to the same number of things. Okay? Just like a dozen. When we describe something as a dozen, what does that mean? There's 12 of them. You can have a dozen donuts, or you can have a dozen eggs, or you can have a dozen school buses. It's still 12.
What if you have a dozen cupcakes? Would it be 15?
No, that would be a baker's dozen.
Still a dozen?
You would have to describe it as a baker's dozen, right? That's different, okay? But one thing that would be similar though, a baker's dozen is always how many? 13, right? So when we describe something as being a mole, we're always talking about the same number of things, right? It's a description for a number of things. We can have a mole of school buses. It would just be this many school buses. It's a lot of school buses. Okay. So, just for some perspective as far as what kind of a number we're dealing with here, okay? It's huge. This is how huge it is, right? So, on average, it takes a normal person about a minute to count to 100. Okay? You don't have to start counting to 100 and time yourself, all right? It's on average, okay? So it takes an average person about a minute to count to 100. Sure, you could do it faster than that, or you can do it slower than that. So about on average, a minute, okay? Counting at that rate, 100 every minute, it would take, I've done the math before, I can't remember off the top of my head, but it it would take like 75 years to count to that number. And that's like continuously counting, though, not stopping to sleep or eat or things like that, right? So that's what we're talking about here. Yeah, I told you you didn't have to count to 100. So we're talking about a huge, 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 huge number because atoms are so small. We need a huge number to get to an amount that we can actually work with in the real world. Okay? So, how does this all fit together? Well, because a mole always equals the same number of things, we can use it in a conversion factor. Remember, conversion factors don't change the amount of something, they just change how we're representing it. If we have 1 mole of atoms, we have 6.022 times 10 to the 23rd atoms. It does not matter what kind of atoms we're talking about, because a mole always describes a number. It doesn't matter what we're describing, it just describes that number. Okay? Now, we said that if we had the same number of things, atoms, those atomic masses on the periodic table, comparing those atoms to carbon-12, the relationship would be the same as long as we had the same number. So, if we have 6.022 times 10 to the 23rd atoms, we have an amount equal to the molar mass of that element. Now, notice, molar mass is in parentheses, okay? 6.022 is always the same number, regardless of how many atoms we are talking about. Sorry, that's the wrong thing to say. 6.022 is the same number of atoms, regardless of the kind of atom that we're talking about. But are all atoms the same size? No. So if we have the same number of atoms, how much those atoms weigh depends on what kind of atom we're talking about. The molar mass of an element is how much the same number of those atoms weighs. We get the molar mass from the periodic table. That number, the average atomic mass that we were looking at earlier in the week, that number is the molar mass. So, when you look at the periodic table and you find magnesium, magnesium has an average atomic mass of what? Nope, that's the atomic number. What's its 24.305. If we put 6.022 times 10 to the 23rd magnesium atoms on a balance, it'll say 24.305 grams. Okay? Then, a little algebra here, right? If A equals B and B equals C, what has to be true? So 1 mole of a substance is equal to the molar mass. That's why it's called the molar mass. Now, these terms are completely new to you. I doubt that any of you have ever heard of them before. Okay? Maybe the mole, but you might not have understood what it meant. But the fact that they are equal to each other means that we can use them in a conversion factor. Right? Because conversion factors, top and bottom, have to be equal to each other. For example, let's just do this quick calculation down in the space at the bottom of your outline on the back page there, right? There's like half of a page is completely blank. All right? For the purposes of this video, Come on, visualizer.
What if it doesn't load this time?
Oh, it'll
What
load.
do you do?
Don't you worry. Okay. Okay. Nope. Nope, wrong way. Oh. Don't worry, we just have to look at the number. Wow. Okay. So, here is, actually let's do this. Good thing we're getting all this. Good thing we're getting all this on camera. Okay. Oh, wrong way. So I know. Oh, this is terrible. This is so bad. Sorry, everybody. Okay. Wow, that is terrible. No, wait. Wait. Haha. There we go. Okay. All right. So here is a balance. I'm going to zero that balance out. Okay? Here, in this Ziploc bag, if I can get it open, is a roll of magnesium. Okay? So this is, no, it's magnesium. Okay? So it does kind of behave like a slinky, right? If you can, you always will. All right, so here's a roll of magnesium. All right. I'm going to put this magnesium on the balance, and it's going to show us that that roll of magnesium has a mass of 22.77 grams. So let's set ourselves up a conversion factor so we can figure out how many atoms of magnesium are in that roll. Okay? All right. So, here, even though we don't have a problem to work off of, what am I asking us to calculate here?
Atoms.
Okay. Now, one thing that I will make a suggestion for you moving forward. As we start doing more problems dealing with elements and different types of atoms, it will help you keep things straight if, after we talk about the unit, give me the element that we're talking about so we know like atoms of what. So we're trying to find how many atoms of magnesium are in that roll. Do you remember what the mass of the roll was? 22. Okay, so 22.77, I believe, right? Let's pull the visualizer up here. Okay, there it is. Yeah. All right. So we have 22.77 grams of magnesium. Okay? Now, converting this value into atoms isn't going to change the number of atoms of magnesium that are on that balance. We're just representing the same amount in a different way. Okay? So, it's time for a conversion factor. We can put this original measurement over 1 if we would like, just to make it a little simpler and easier to understand the math, right? Then, times sign, fraction bar. Okay? When we're setting up the conversion factor, units first. What unit has to go on the bottom of this conversion factor? Grams of magnesium. Right? What unit should go on the top of this conversion? Atoms of magnesium. Now, let's go back. Well, you guys have it in front of you because you're doing it on this page. But what did we say has to be true about the top and the bottom of that conversion factor? They have to be equal. Which one of these 3 bullet points should we use to make the top and the bottom equal to each other?
The middle one.
The middle one, right? in all three of these equals here, right? Equalities. What number comes in front of atoms whenever it shows up? It shows up twice. What number always? 6.022 times 10 to the 23rd. It does not matter what kind of atom we are talking about. If atom shows up in a conversion factor, we always talk about the same number of atoms. And that number is 6.022 times 10 to the 23rd. So, in our conversion factor here, we'll go 6.022 times 10 to the 23rd on the top of this conversion factor. Okay? Now, in the second equality, what does it say that that number of atoms is equal to? The molar mass. Grams, but a specific number of grams, that being the molar mass. Where do we get the molar mass of an element from?
Periodic table.
We get it from the periodic table. So you go to the periodic table, you find magnesium, and you get its molar mass, which is 24.305. There's a reason why I asked that earlier in the period. All right, so now we can start doing some math, right? Units first. Grams on the top, grams on the bottom. Just the unit, not the number. Okay? Now we got some math, but we have a big number that we have to worry about here, 6.022 times 10 to the 23rd. Your calculator knows how to do scientific notation. I highly, highly recommend that you learn how your calculator does scientific notation. I know how your calculator does scientific notation, so if you don't know, ask me and I'll show you how. Okay? So, if you have a TI calculator, okay, which most of you do, you can, but sometimes though, if you don't use your parentheses properly, order of operations will get messed up and you'll have like the right number, but you'll be off by like a 0 or 2. Okay? So, if you have a TI calculator, okay? Alright, we'll work on this tomorrow as we work on it tomorrow. You'll have to live in suspense until tomorrow. Alright, we'll finish up this practice stuff tomorrow and do a lot more practice.